And so we look at these masers throughout these star-forming regions and use them as bright point sources, basically. They're just useful.
Question?
Yeah, let me just finish this thought, though. People have been surveying the Andromeda galaxy for masers. And there is star formation going on in Andromeda. Not quite as much as in the Milky Way, but there's plenty of star formation. We have not been able to detect a good enough maser to use as a point source in that galaxy. Surprisingly, actually. So there was a question?
If the Milky Way has whatever is X times more mass than originally thought,
50% more.
then shouldn't that have been noticed in the calculations as far as gravitational attraction between us and the local group?
No, because you don't know masses of anything, basically, in an absolute way. So, we don't really know the mass of Andromeda. First you have to know its distance, you have to know the rotation speed. You can only measure the rotation out to this distance, and these dark matter halos go much further out. So then you get into the realm of theory to try to get the mass.
So you can't use like the same principle that you think of when you're looking for like exoplanets or even like double stars, I guess.
No, I mean what you have to do is measure the rotation speed of something, the orbital speed. Okay. And you can do it out to some distance in Andromeda, but not far enough. And in the Milky Way, the problem, why is this changing by 50%? It's because we're inside a rotating system, and it's just very hard to get an absolute measurement. Everything you measure is a relative measurement, and it's not highly sensitive to the rotation speed. It is sensitive, but not highly. So it's a tough measurement to make.
How would you differentiate your gas component velocities relative to the true orbital velocity?
Yeah. So the gas we're talking about for these masers are little clouds of sort of planetary scale mass around very, very young stars, usually O-type, 20, 10, 30 solar mass stars. These clouds of gas, there are many types of them. There's water masers, so water molecules are emitting laser light, methyl alcohols emitting laser light, and some other molecules. Turns out that these are generally bound to the stars, these clouds, especially the methyl ones, methyl alcohol ones. And so they're moving very slowly with respect to the star. So a measurement of the motion of one of these clouds gives you the motion of the central star that it's attached to within a few kilometers per second, which is good enough for all of this. But yeah, you have to think about that.
Right. How do you know it's moving slow relative to the star?
Okay. Basically, you measure, you see lots of these clouds around a star, and in the methanol you can see that the relative motions of all these clouds are very small. And you sort of assume it's binding it, and you can't see it. You can't see the star. Yeah.
Is this similar to measuring when you have an active black hole? Because there's inactive black holes, right? When you have an active black hole, you can see the stars moving so rapidly, their velocity around the black hole is increased when the black hole is active, right?
No, that's not true.
That's not true.
No, stars, so for example, in the Milky Way, we have about a 4 million solar mass black hole at the center.
Yeah.
And infrared astronomers have been able to actually see stars that are they get within about 100 astronomical units of the black hole, so roughly solar system scale. And these stars are observed, but that's all they're in gravitational orbits, elliptical orbits around the black hole. And when the one star that gets the closest that's been measured is at pericenter in the orbit, the closest point in the orbit, it's been observed to move at about 5,000 kilometers per second. It's getting to be a fraction of the speed of light. It's quite impressive. Now, that's all gravitational. It's just an orbit about a massive object. So when the black hole is active, it doesn't really change that. The stars would never really notice it. Now, if we were on a planet near one of those stars and it became active, we'd get a lot of radiation. We wouldn't like that.
But wouldn't you see that more with your telescope if they were active? Wouldn't you get more accurate measurements?
Okay, so we could try to take and look at the black hole, the emission from the black hole, which is a little complicated because it comes from around the black hole and not the black hole. And then you can try to measure, you're saying, the wobble of that with time. Okay. I've been trying to do that for the galactic center black hole, to actually get its parallax directly, to get the wobble induced by our changing vantage point. Because the galactic center is very far in the south, it really hurts us because we're looking through a lot of atmosphere. If we could take our VLBA, Very Long Baseline Array, from the northern hemisphere and move it to the southern hemisphere, we could do that measurement.
How do you do that?
Well, it costs money. Okay. But now to measure the wobble induced by a star that's orbiting. So it's like a planetary wobble. That's even harder. But we've been able to put a limit on the motion, the speed of Sagittarius A star, which is this black hole, of about 1 kilometer per second. It's sitting at the center of the Milky Way and not moving to about 1 kilometer per second accuracy, which is really a pretty slow speed. Right? The Earth goes around the sun at about 30 kilometers per second. And if you go to the Smithsonian Museum in Dulles Airport, you'll see the Blackbird. It's this, the U-2 basically. Blackbird, which is one of the fastest planes ever built, and it's gone that fast. It goes 1 kilometer a second. So we made things that go that fast, that fly. So basically, we cannot detect the wobble from a star that's orbiting it yet. That would be a very, very difficult measurement because the star weighs, say, a few times the mass of the sun, and the black hole is a few million. So it's 1,000,000 to 1. And so it's hard to do. But they're interesting measurements. I've been trying to do some of those. Some are harder than others. These parallaxes are actually kind of easy. It was because, actually, I was trying to measure the parallax of Sagittarius A star. I worked on techniques to try to improve the accuracy that led to these parallax measurements. Any others?
We don't fully understand the mechanism which holds the galaxy together yet.
Well, you're talking about dark matter?
Dark matter is the current plug matter. Is the current the plug in order to make it work approximately.
Things are moving around too quickly gravitationally for the mass we see in light and the stars.
Right. And why the arms are there is still a great question.
That's a good, there are a lot of theories. There was an active field of study to predict why are spiral galaxies spiral. How does that work?
In time they should have.
One thing is the wind-up paradox. That is, okay, the Milky Way is spinning this way. And if you think you just took the center here, grabbed the bar and just turned this pattern you would think would wind up very tightly. As the thing spins. And it would have had about 100 winds within the age of the Milky Way. So that doesn't happen. So these things are not like clock springs or gears. These are really waves that sort of almost look the same at almost any time, we think. But that theory was developed in the 60s and 70s. There's never been really good data to test it. And so people sort of gave up on that. They were sort of before good computers, so they couldn't simulate a galaxy numerically. So I think there'll be a little rebirth of study of spiral structure in galaxies now that we can compute that as well as measure things in galaxies.
Okay, one last question. Okay, Dr. Reid will be around during a break. I'd like to thank you. Wonderful.